Good morning, dear students. Welcome to another session of digital switching systems. In this session, we'll be looking forward for switching system aspects. In relation to this, we'll be covering a few of the topics which are related to introduction of the switching systems, then single stage networks, gradings, then link systems, and the grade of service of link systems. So starting off with the introduction part, so whenever we speak of telecommunication systems, we need to concentrate on a few of the things as to how the telecommunication system has to be designed. Now, whenever we speak of telecommunication system, another aspect which comes is how an interconnection has to be established between a calling and a called party. So in order to do this, we have to look forward on how the switching networks have to be established. So these are the basic things what we have to look out when we are dealing with telecommunication systems. So in this prerequisite says the design and construction of the switching systems and what type of switches will be using and how they'll be utilized, and apart from this how we have to handle the traffic which has been generated by the users. So these are the prerequisites of a telecommunication system, and related to this there is another parameter, that is what are the functions which are related to the switching system. So basic function of a switching system is nothing but establishing a connection between a called and a calling subscribers. This is basically done with the help of a incoming trunk and outgoing trunk. So that we have to establish a connection between an incoming trunk and an outgoing trunk, say via using a switching element. So this is related to introduction part. So let us move on with the single stage network. Now here we can see that in the figure we can observe few things, that is in this figure we have M inlets and N outlets. So what is this basically doing is, if I specify M as the incoming, M is related to the incoming calls and N is related to the outgoing trunks, then any incoming call on these M inlets has to be connected to one of the outlets which is present on the N outlets. Now this is done with the help of what is called as a switching element, which is basically a relay kind of system. It may be a mechanical relay, it may be a electronic relay. So these are the things what can be utilized. Now what does this specify is, you can see that in this one, if I want to connect any one, say for example, if I want to establish a connection from this point to the other point at the outlet, then I have to be operating this relay. Now if I have to operate this relay, it is nothing but I am operating what is called as a cross point in telecommunication system. So cross point is one of the major concepts which we have to deal with the networks what we are studying here. So this is a single stage network. So later on we'll check out what is meant by a 2 stage or 3 stage or 4 stage. In the same order we can have n stage networks. So since here you can see that there is only one configuration which is present, so in this case this is termed as a single stage network. So that is what this figure shows us, and apart from that we dealt with what is termed as cross points. Now in this case I can have actually three parameters which are possible with respect to M inlets and N outlets. So with respect to this, what it implies is I can have M equal to N is the one possible thing. So apart from this, I can have another parameter, that is inlets is less than the outlets. So what does this imply is, this gives us what is called as a expander. Then apart from that, if inlets are more compared to the outlets, so that is what is this equation specifies, then it gives rise to what we term as concentrator in telecommunication system. So we'll be dealing with this and the design of single stage, design of 2 stage, 3 stage and 4 stage networks in the later on topics. Now apart from this, what is the symbol which is used to represent this kind of cross points or the switches which we are operating? So you can see that we have the representation of switches which is given in figure 2.1 1. So these are symbols which are used. So it is for simplicity, it is not feasible to draw this diagram every time for all the networks. So in order to simplify that, we can make use of these symbols in our explanation. Now apart from this, in this diagram you can observe that there is a circle which is represented here. So what does this circle imply is, this circle implies that this is the inlet. This is the inlet side and the other one is the outlet side. So this is another symbol which is used to represent the switches. So in later on we'll be using these kind of symbols to represent the switches as and when required. As we go on with more number of stages, it becomes tedious to represent the stages using such kind of cross points or such kind of switch elements. So therefore we make use of these symbols. So that is so here if I just specify the cross points, in this case when I consider in the single stage network, in this case the number of cross points is basically nothing but how many elements are present in order to make connection from an incoming to an outgoing line. So in this case, if you just make a simple mathematical logic, then it is nothing but the number of inlets into number of outlets. Now it is termed as C1. So this subscript 1 implies that it is single stage network. This cross point is related to single stage network. Now here another important thing to observe is I do not require all the switches to be operating in order to make the connections. So in what does this imply is that more than half of the cross points are not necessary, so they are redundant. Now what does this imply is, it implies that if I want to establish a connection from say inlet 1 to outlet 2, the same operation can be performed by using the inlet 2 to outlet 1. So that is 1 comma 2 does the same operation as 2 comma 1 cross point. So therefore what we can do is we can eliminate the other cross points and we come up with the other configuration which will be dealing in the next slide. So related to this, now if m is equal to n, then what does this imply is it gives us the number of cross points which is n square. Now here another parameter to imply here is the cross point gives us a rough estimate of the overall cost of the system. So basically if I have to deal with the cost and I have to reduce it, then my intention will be to reduce the number of cross points, whether it is a single stage, 2 stage or 3 stage or any number of stages. My intention is always to optimize the number of cross points or minimize the number of cross points. So that is what we'll be looking in further slides. So cross points also gives us a hint on the rough estimate of the switching systems. So here we can just observe that if m is equal to n, C1 is proportional to n square. So what does this indicate is the cost also increases as the square of the number of inlets or number of outlets in the case of m equal to n. So that is one major factor what we have to look out. Therefore if I specify the efficiency related to a single stage network, it is basically the ratio of number of trunks which are available. So in this case it is the number of inlets or the outlets, since we are considering m is equal to n. So if I specify, it is the number of say outgoing trunks divided by number of cross points. So what is happening is the overall efficiency turns out to be 1 by n. Now here we can observe that efficiency is inversely proportional to n. So what is happening if n keeps on increasing? If n keeps on increasing, so in this case what happens is efficiency keeps on reducing. So that's why we have to take care that the number of cross points is reduced. So indirectly what I am indicating is we are trying to increase the efficiency of the overall switching system. So in the previous slide I just spoke that not all the cross points are required to establish the connection or make the network work. So in this case if I just take a simple example that the cross point j comma k performs the same function as k comma j. If this is true in this case, then what happens is, and which is true in this case, and what happens is we can eliminate few of the cross points which are not required. So if I remove that, what happens is I'll be ending up with a matrix which is shown in this form. So this is called as a triangular cross point matrix, and in this one more than half of the cross points are eliminated. So in if I have to make observation related to this, that is how many cross points are available. So if I just observe, it is a mesh kind of network, so therefore the cross point for the single stage network using triangular structure will be n into n minus 1 divided by 2. So you can see that there is a change from n square to n into n minus 1 divided by 2, that is, it is almost less than the half which was required in the previous case. Now here another thing to observe is this is a kind of asymmetrical configuration. So generally when we are designing networks, we do not prefer to go for asymmetrical kind of networks. We go for symmetrical kind of networks and then go ahead with the design. So even though this is reducing the number of cross points, but designing these and other things becomes a tedious process, and it may involve a lot of time, and so due to which what we do is we generally avoid using such kind of structures. We make use of the previous structures what we have designed, but based on some specification we try to reduce the number of cross points which are required over there. So moving ahead, next one we have gradings, that is the principle related to grading. So before going into this aspect, we should understand few things which are related to grading and the design of these switching systems and other parameters. So first of all, the term which comes is availability. There are three terms and all are related to each other. That is, for example, here we are dealing with availability, then we deal with something called as limited availability, and then we term with what is called as full availability. So in order to understand this, we can refer to these diagrams, that is 2.3 and 2.4. So these are later used in problems. So just for understanding purpose, we'll just discuss these things. So what does availability specify? Availability specifies that it is the number of outgoing trunks to which an incoming trunk can obtain a connection. Now what does this imply is, now later on we'll just try to understand what is meant by groups. So at present we'll not bother about that. So first I'll consider, say, just the group 1. I'll consider only group 1. Say group 2 later on we'll just check out. Now if I just consider group 1, say group 2 is not there in the present scenario. So in group 1, I can, any incoming call on this trunk can access these 10 outgoing trunks via the switch. So these 10 outgoing trunks which are available to the incoming trunks to which the connection can be established is termed as the availability. So availability is just a number which tells you how many outgoing trunks are available for an incoming trunk. Now here one interesting fact to observe is, now if I refer to the same this thing and come to this here, there is a slight change. Here you can see that in this case I am not having any common connections between the two groups, but here I am having some common connections between the two groups. So later on we'll understand why this is done and what is the feasibility and what happens overall in this case. So availability just gives me, for a given incoming trunk, how many outgoing trunks are available. So that is the case. So in this case I am having 10 outgoing trunks, so availability is equal to 10. That's why what we have specified, it depends on the switch outlet. So this switch can make connection to 10 outlets. So that is what it specifies. Therefore availability also can be identified based on the outlets which are present for the switches. Now next, coming on to limited availability. So it the name itself tells that it is limited. That is, number of outgoing trunks, only specific number of outgoing trunks are accessible to the incoming trunk, then it identifies it as a limited availability, and these available trunks are sufficient to carry the traffic. That is what it intends. So each incoming trunk has access to a sufficient number of trunks on each route to give the required grade of service. Now out of this, if I just take an example of this case, in this group, say suppose only the first 6 are available for me to access and remaining 4 are not available, that is they are not present in the scenario. So then what it implies is out of the 10 only 6 I will be able to utilize. So this is what is specified as limited availability. Then comes what is meant by full availability. It specifies that we have full access to all the trunks which are available. Now let us consider this entire thing now, so which has basically 2 groups. Now in this case, what we have to look out is, if you just observe, so if I just observe here, if I just count the number of trunks which are available here, so it is total 20 trunks. Now on this group, the incoming trunks has access only to these 10 trunks, but these 10 trunks it is not available. So this is what is actually limited availability. Now in other case, now if this switch gains access even to these 10 trunks, so if any incoming trunk can access all these 10 trunks plus these 10 trunks, so then it indicates that it is having full availability. So this is what is meant by full availability. So limited, out of these 20 trunks only 10 trunks are accessible, so it is limited. If out of these all 20 trunks, if all the 20 trunks are accessible, then it gives what is meant by full availability. So next thing what we have to look is what is meant by grading. So in grading, it implies that it is a technique which is used to interconnect the multiples of the switches. So basically if you just look at this, this is a kind of grading, and here this is also a kind of grading. So here you can see that these outgoing trunks are connected in some fashion, and here also the outgoing trunks are connected in some fashion. So this is nothing but grading, how the connections have been established between the incoming and the outgoing trunks, so via the switches. So that is what it specifies, the technique what we use in order to interconnect these multiples of the switches. So there is one switch here and one switch here, the multiples of these switches in order to connect, that technique is specified as grading. So this one we'll be looking later as to how it is specified, wherein we'll get to know through a problem. Now this is also called as Odell grading, and another thing is we come across another term which is called as progressive grading. Apart from this, we have different kinds of grading, so that we'll be dealing later. So what is meant by progressive grading? Now for example, if I start off with say group 1, and I have a switch which has access to these 10 outgoing trunks. So in this case, whenever a call comes or there is an incoming trunk, and the switch, what it does is it tries to check from the sequential point of view. That is, it checks first the first outgoing trunk. If the first outgoing trunk is busy, then it moves on the second. If second is busy, it goes on to the check. It goes on to check for the third one, and so on. It continues until it reaches the last one, or it gets any access to a free trunk. So this kind of search is search which is related. That is a sequential search. Any grading which makes use of such kind of search is classified under progressive grading. So that is what it implies. So in simple, switches which hunt over the outlets in sequential form gives us what is meant by sequential grading. So moving on with the next part. In previous session we had solved a problem wherein for a given grade of service for both incoming and outgoing calls, we had to identify how many a group of lines were required if both had to be handled separately, that is the incoming and outgoing calls had to handle separately, or and what is the number of outgoing lines if both incoming and outgoing calls were handled in common. So we had seen some solution, that is we had observed that if both are operated separately and using the table, full availability table, we saw that 4 airlines of traffic required 10 lines and 10 airlines required 18 lines. So total of 28 lines were required to handle the traffic separately, that is for outgoing and incoming traffic. Now if it was on common, what had happened, you can see that only 23 lines were utilized. So this is, you can see that there is a change in the number. So here it is 28, but for the same traffic, but when it is handled in common and for 14 airlines, 23 lines are required. Now why there is a difference of 5? So it is related to the previous case. Now let us come to so let us observe here. So here you can see that there are two groups in which I have 10 trunks here and 10 trunks here. Now in this case, what is happening is if I say provide some traffic to this, say about 8 airlines of traffic, so these trunks give me a grade of service. Let me specify it as 0.01. So grade of service provided using this configuration is 0.01 and it is capable of handling 8 airlines. Now when we look at the design table, what it implies is this: if I provide the same 8 airlines of traffic to this case, then only 16 number of outgoing trunks is sufficient to provide me a grade of service of 0.01. So same grade of service but with lesser number of trunks, same grade of service but with higher number of trunks. So it is preferred to use this one which is making use of less number of trunks. So that is what we look out for. So that is how in your previous problem, to handle 14 airlines of traffic in common, we required just 23 lines, whereas handling it separately required around 28 lines. So it is all because of these 4 common connections which are present here. So if I observe based on some design, we have to decide on how many commons will be there. So if I just observe, I have first 6 trunks which are available to group 2, and there are another 6 trunks which are available separately to group 1. Now if I just observe, these 4 trunks and these 4 trunks are in common, and these can be accessed either by group 2 or by group 1. So these are the commons. So because of this common structure, what happens is here group 2 has access to total number of 10 trunks, group 1 is having access to total number of 10 trunks, out of which these 6 trunks are given separately to group 1 and 6 trunks are given separately to group 2, but 4 trunks are given in common to both. So this is what is happening in this case, and this is giving me the same grade of service for the same traffic. So this is the preferred design which is making use of less number of trunks as compared to this case. So therefore I go in for this parameter. So let us stop this session today for up to this point. So in the next class again we'll be continuing with the next part. Okay, thank you and goodbye for today.